Hi, I'm going to do a video now on coherence. It's a difficult one, coherence. It's a difficult one to spell. Look, I've even missed a C out there, but hopefully that means you won't. Coherence. Difficult one, really. And I think what we'll try and do is build up why we need the word more than the word itself to start with. So, interference pattern diagram, just like you've been seeing before. And I've sort of pre-arranged this. It's not beautifully drawn, but this point here we can imagine is constructive superposition, because we've got, if we take the solid lines as being peaks, we've got a peak from one source and a peak from another source. And we've got constructive superposition. It turns out that that distance there is a wavelength further than that distance there. So we're in phase and we've got a constructive superposition. And here we've got destructive superposition, because we've got a peak from this source and a trough from that source, because that the path difference is now half a wavelength. These waves become half a wavelength further. But to actually form this pattern, two things need to be true, really. One is the wavelengths need to remain consistent, and the rate at which the two places produce their waves being consistent, because we're not just saying at this moment there is constructive superposition. We're saying for all the time we see the pattern, there's constructive superposition. And that puts some really tight constraints on these two sources. And the most obvious thing to say about those two sources is that they should both produce a peak and both produce a trough at exactly the same moment. And that would work. It would mean they had the same frequency, and then that would mean the waves had the same wavelength. And you can see it's important that both sources have the same wavelength. It turns out that we don't have to be quite that strict. It wouldn't matter if this one made a peak and this one made a trough exactly the same time, provided the phase relationship between the two remains constant. Okay, so we've got to have a constant phase relationship between our sources. So two sources are coherent if they have the same frequency and they have a constant phase relationship. Now, if you really think about it, if they've got a constant phase relationship, if the phase relationship between the two is pi radians, they're constantly out of phase, then they have to be the same frequency. So this is really the important thing about the important one for defining coherence of two sources. Where it gets slightly more complicated is it's not just sources that can be coherent. Waves themselves, actually areas of waves, can be coherent and incoherent. And if you ask me to put it in simple colloquial terms, ordinary everyday language, I'd say organised waves. If we imagine two aerial views of waves, the sort of waves we see in the sea. If in one picture we see each one of these lines represents a wave crest, they're all going that way, they're all parallel, then these are coherent waves. If they're travelling in different directions and they have different wavelengths at different times, then these are incoherent waves. And one reason why waves might be incoherent is they might have travelled different distances. So what I'm going to do is I'm going to run through a specific example of where we need to create coherent waves as a way of explaining the word coherence, and then I'll give you the kind of textbook definition, even though I find that a bit verbose and wording. Now, when I demonstrated the interference pattern you see when light travels through two slits, I had to use a laser. A laser is a coherent source of waves. So what I mean by that is the light coming out of a laser is organised in this way. The light from an ordinary bulb is more like this, and it's actually very difficult to produce nice coherent, nice fringes from a bulb. So if we have a bulb, and this is in the specification, the setup for using a bulb or an incoherent light source to produce fringes is in the specification. The first thing that needs to go through if you're going to make fringes is we need a filter. Okay, so a coloured filter, so that our white light becomes monochromatic, becomes all one wavelength and hence all one frequency. So this is our coloured filter. But you can see the waves here of all. This filament is, every part of it is producing waves, and because they've all started in different places, by definition these waves are going to be incoherent. So what we do is we put in a single slit, and now that single slit will act as a single point source of waves, and that will increase the coherence. So we can imagine our waves, our jumble of waves left, I won't try and draw, these neatly spreading out as coherent organised waves. They will then illuminate two slits. The light will diffract through the two slits, and that's the light from that slit, that's the light from that slit, spreading out by diffraction. We will only see right fringes in this area where the light overlaps from the two slits, because we have to have light from the two slits to form an interference pattern. So that arrangement isn't the specification. So, but for the purposes of today, we made our light coherent by making it monochromatic and diffracting it through a single slit so it acted as a point source. Those nice neat wave fronts will hit both of those slits at exactly the same time, meaning these two, in this way I've drawn it, will be both coherent and in phase. But if we twisted it an angle, and so it hits that slit, then that slit, that doesn't matter, because they'll have a constant phase relationship between the two, and the two sources will be coherent. So the wordy definition is waves are coherent if all parts of the wave front have the same phase, which is wording you might need to reproduce. It doesn't intuitively ring with me. If we go back to this diagram here, I can sort of explain it. So we've got to imagine that behind here is, these are the waves. So that's a cross section through the waves here. Here's a cross section through the waves here. This part of the wave here and this part of the wave here, they've got the same phase. So all the way along there, because it's a straight line, every part of the same wave has the same phase. If this wave front did that, then this part of the wave would have a different phase, and that would make it incoherent. Okay, thank you with that. All the best.